Okay, as I said, we will start now, even though people can still join in as we go. So, welcome all to the 7th episode in a series of webinars showcasing the uses and benefits of Copernicus, the Earth observation component of the EU space program. My name is Sofia Oterugo-Mono. I'm part of the Copernicus Support Office, and I'll be your moderator today. This 7th webinar looks at how Copernicus data can be used for monitoring and protecting the ozone layer and its impact on public welfare. I should mention that this webinar is being recorded, and we will share the recording on the Copernicus EU YouTube channel. To make the webinar a bit more interactive and to get you to engage with our speakers, we will be using Slido for live questions. If you have downloaded WebEx, you will find Slido on the right-hand side of your screen in the Apps tab. If you're joining us directly from your browser, you can access Slido using the link that we shared in the chat. You may respond to the questions that will pop out on Slido as we go. And also you may ask questions yourself based on the content presented today. So feel free to type in your questions so that we may answer them during the Q&A session after the presentation. So as an initial icebreaker, we have already started with one Slido question, which is, what sector do you currently work or study in? So for today's agenda, we're spicing things up a bit with respect to our usual webinar format. So today our two speakers will be giving a joint presentation, each of them focusing on their area of expertise. You will be hearing from Vincent-Henri Peuch, Director of the Copernicus Atmosphere Monitoring Service, and from Sara Basart, Science Officer at the World Meteorological Organization. Following their presentation, as always, we will open the floor to you, the audience, to ask any and all questions that you may have. So please feel free to type them on Slido. Now, before I introduce our speakers, let me open a second question that we have for you. We're actually curious to know what brought you to this webinar on Copernicus for public welfare through ozone layer monitoring and protection. Now, as you reply, and without further ado, I would like to present our speakers. We have Vincent-Henri Peuch. He is Director of the Copernicus Atmosphere Monitoring Service and Deputy Director of the Copernicus Department at ECMWF. He oversees the management, technical, and scientific activities that allow for the delivery of information products about atmospheric composition to users. He has been involved in the design and development of the European Copernicus program for over a decade. And before joining ECMWF, he conducted research for 15 years on atmospheric composition modeling and data assimilation at Météo France, pioneering on air quality forecasting in Europe. We also have today Sara Basart. She's Science Officer of the Global Atmosphere Watch Program within the Science and Innovation Department of the World Meteorological Organization. Sara holds a PhD in Environmental Engineering, and she has over 10 years of experience in research, mainly focusing on mineral dust modeling, air quality, and aerosols. Before joining the WMO, she was a researcher at the Barcelona Supercomputing Center and lead scientist in the WMO Barcelona Dust Regional Center. Now, Vincent-Henri, Sara, the floor is yours.
Thank you, Sophia. So let me share my screen and video mode. Is it all right for everybody?
Yes.
Perfect. So thank you very much. So in the coming 40 minutes or so, together with Sara, we'll talk about the ozone layer. And I will start immediately by introducing ozone. So you've certainly heard about oxygen. Maybe you've not heard about ozone. However, I think we will convince you that it's a crucial constituent of the atmosphere. So if you look at this picture here on the left, you see this line which describes the amount of ozone in the atmosphere from the ground up to the upper atmosphere. Actually, ozone is present throughout the atmosphere, but it's formed by very different sets of reactions, whether you're in the high atmosphere or closer to the ground. So today we will be focusing on the ozone layer, which sits in the stratosphere, so about 25 kilometers above ground. And actually 90% of ozone in the atmosphere is in this ozone layer. Just for completeness, I mentioned that there is also ozone lower down, and you've probably heard in summer of ozone pollution episode. So there, ozone is rather bad because it has impact on health, on ecosystems, and it's created through chemical reactions from precursors, part of them being of human origin. And ozone in the lower atmosphere, in what we call the troposphere, is also a greenhouse gas. So having lots of ozone in the troposphere and near the ground is actually not good. Conversely, it's the exact opposite in the stratosphere, as the ozone layer is actually protecting us humans, but also all the living things down the earth, because it filters the part of the incoming solar radiation, and particularly the most energetic and most dangerous part of the atmospheric radiation. So you have this little graphics on the right that shows the solar radiation that arrives at the top of the atmosphere as a function of wavelength. To the left, you have the high energy wavelength, starting with gamma rays, UV, and then you go into the visible light, and then you go to the infrared. And what you see is what comes through the atmosphere is only a fraction of these, because atmospheric constituents like CO2, water vapor, and ozone and particles, they filter out some of this radiation. And ozone is very critical in filtering out the part that is in the ultraviolet. Actually, it filters very effectively most of the radiation that has a wavelength smaller than 280 nanometer, which are very, very dangerous. As I mentioned, ozone is actually a super important atmospheric constituent, and arguably more important than oxygen. And to substantiate this statement, here is a little graphics which shows as a function of time, starting 46,000 million of years before present in the Precambrian period, up to some millions of years today. As a function of this, it's the percentage of the abundance of ozone in dashed line and oxygen in full line as a function of time. So you see that ozone and oxygen started to increase about 40,000 million years ago. And as the two gases increased in the atmosphere, life evolved. And what you see, I would like to focus at the end of the Precambrian period, so about 600 million years ago. At that time, mind the scale is logarithmic. At that time, oxygen was just about 10% of the current amount of oxygen, so very, very far from being what we experience today. But ozone was already close to 80% of the amount that we have in the ozone layer. And even if oxygen was low, because ozone was already pretty close to now, it's really the turning point when life started to move out of the sea and start developing on land. So really, in the history of life on Earth, the formation of the ozone layer was really pivotal in the development of life. So that's very good, and the ozone layer has protected the Earth for a very long time, until the 70s and 80s. And these pictures, which are reproduced, of course, they were not available at the time. I will explain later how they are made. In spring over Antarctica in the late 70s and 80s, the ozone layer started to reduce and diminish. So we have in ozone, we have a unit to characterize the thickness of the ozone layer. This unit is called the Dobson unit. It's simply proportional to the number of molecules of ozone that you have between the ground and the top of the atmosphere. Generally, the thickness of the ozone layer is of the order of 300 Dobson units as a global average. But in spring, over the southern pole, the ozone layer was normally of the order of 400 to 450 Dobson units, so colors of orange and red and brownish. However, starting in the late 70s and 80s, you see these blue colors happening, and the black line actually delineates the areas where the ozone layer is less than 220 Dobson units. And very rapidly during this decade, it was seen that every year, around September and October, the ozone layer was being destroyed by something that was not known at the time. So behind the understanding of what was going, there is a number of people that allowed to understand what was going on. I will first mention Paul Crutzen, Mario Molina, and Sherwood Holland. The three of them got actually the Nobel Prize in Chemistry in 1995 for understanding these processes. It started with Paul Crutzen starting to reflect on, in particular, high-flying aircraft, so the Concorde, etc., and the potential of these aircraft to include constituents, chemical constituents in the stratosphere, and he was questioning whether this could be a problem for the ozone layer. While Mario Molina and Sherwood Holland studied first in the lab that certain chemical constituents that are very stable on the ground, if they made their way to the stratosphere, they could be depleting ozone. However, the calculation at the time was that if there was a depletion from nitrogen oxides or from these chlorine containing compound, which are called the CFCs, it was something that was thought to be watched, but not something dramatic. And then came the British Antarctic Survey with Joe Farman, Brian Gardiner, and John Shanklin, who actually were measuring the ozone layer in Antarctica with an instrument like the one that you see here. And what they observed actually in the winter and spring of 1984 was that there was an unexpected, very large depletion of ozone. So that's a plot that I showed you on the previous page. And they started to hypothesize that the very cold and isolated condition in the stratosphere during the polar winter and the spring, combined with the presence of chlorine and bromine compound as identified by Molina and Sherwood, could be responsible for this phenomenon. And as such, they discovered the ozone hole. Let me hand now to Sara.
Thanks, Vincent-Henri. Yes, it's because this context that Vincent-Henri explained as a background for you, that is it in the 90s was launched this Montreal Protocol on substance that deplete the ozone layer in the landmark of a multilateral environmental agreement that regulates basically the production and consumption of nearly 100 man-made chemical substances that are ozone depleting. Then the agreement was adopted in 60 September 1987. And to this date, probably this protocol is one of the most successful, with more consensus and achieved more universal ratification in the environmental approach. Presently, this is the picture that you can see in the left part. The Montreal Protocol marked a new milestone in 2019, that is the Kigali Amendment. And this amendment is now focusing in another group of substances that are also harmful for the climate, not especially for the ozone depletion, but really connected with the climate change, that are the hydrofluorocarbons, the HFCs. And basically these new reactive gases are coming from the new air conditioners, refrigerators, aerosols, pumps, and other products that are also harmful for the atmosphere. There is a commitment of more than 100 countries to cut the emissions of these new reactive gases over 80% in the next 30 years. Then this is a new milestone for this Montreal Protocol, and also is proof that the protocol was the most successful environmental convention in the last years. And it has not only led the regeneration of the ozone layer, also it is connected with different other goals associated with the sustainable development goals of United Nations, as the protection of the human health, but also the reduction of greenhouse gases, industry innovation, job creation, and more efficient energy use. And because of that, the Montreal Protocol is one of the most priority programs and measures and agreements that are now in the United Nations and is well known by the community. Just to emphasize that this protocol is one of the most unprecedented collaborations, not just at international level, also public and private sectors was committed to participate in the protocol. And then this gives us a really one of the most successful actions at international level, that is this protocol. If you can go next, please. In this context, to establish the status of these potential factors that can damage our Earth system, but also our health, it is important observations. And here, WMO is playing a key role, trying to coordinate the international efforts for the measurement of the atmospheric components and also the trends. It's fundamental to know not just the current present status of the atmosphere, also we have to know how it's evolving along the time and to know the trends. In that way, we can see how the impact of some emissions that are coming from human intervention can affect their climate, their system, and then the future climate. In this context, as I said, it's very important to establish international and global long-term monitoring programs that can support the research done by the scientists and to advancing the knowledge that we have now in the interactions between the different components, the emissions that we produce, but also how these emissions can affect different elements in the atmosphere, but also the ecosystems. And this is basically the main goal of the Global Atmospheric Watch Program, the GO program, that is hosted by the World Meteorological Organization. In fact, GO now is one of the pillars of the ground-based atmospheric composition observations at global scale and one of the key elements for the monitoring of the ozone layer. Basically, these long-term observational records allow us to assist the scientific community for advancing in this knowledge that we have about the interactions of the different reactive gases that are produced by the anthropogenic human-driven emissions with the cause of the ozone depletion, for example. In the article that is showing the slide, you can see a publication from some co-authors coming from 2018, and it was thanks to the support of this long-term monitoring of observations about the different elements, the different parameters that allow us to understand why are the connections between the depletion of the ozone layer and the different components. It was detected that it was reported the production of zero emissions of these CFC since 2006. It was observed through the monitoring of the state of the atmosphere and increase of the emissions of 2012. This was discovered by these authors analyzing long-term series, and it was super useful for identifying that the emissions was not really close to zero by this year. If you go next, please. Then basically, this is one of the goals also of the Montreal Protocol, to put together the scientific community to regularly update the governments and at least the latest scientific achievements and findings related with the ozone layer. This scientific assessment of ozone depletion reports has a frequency of every 4 years, and basically a group of experts with the auspices of the WMO, WHO, UNEP, some US research agencies as NASA or NOAA, and also the European Commission are part of this state-of-the-art science assessment that is basically a guidelines for policymakers, but also for strengthen the original provisions of the Montreal Protocol to assess that the initial goals and the current status of the knowledge and science behind these initial goals are matching and accomplish future goals that should be defined by this community. And the last report is from 2022 and is the 10th edition. As you can see here is the document, and you can download from the WMO website, but also the different United Nations agencies that are involved in this document. And it's basically the compilation of the new published research and findings about the evolution of the ozone depletion substance concentrations, and also the projections that some climate groups are doing for the ozone layer recovery. In the figure here, you can see the evolution of the ozone column. As Vincent-Henri mentioned, this is measured or established by Dobson units, and is the time series evolution from the early 80s up to now. And as you can see here, the two panels are showing the global average, and also the October, that is a month that Vincent-Henri point in Antarctica with the minimum concentration of ozone in this part. That in both cases, we can see how from the early 2000s, the ozone concentrations starts to be up, starts to be recovered a little bit, and the projections also are now constrained for a better scenario in future in which we are recovering the levels of around the 1980s. If you go next, please. Then basically, what the panel that is elaborating this report confirmed the phased out of close to 90% of the ozone depleting substances, and also the report is mentioning the positive impact that this effort is having for climate change and mitigating the effects of the climate change of these elements. Also in the figure, sorry. You can see the evolution of two of these elements, is the chlorine and the bromine, as input into the stratosphere for a reference year. In this case, the reference year corresponds to the worst case scenario in the long-term series that we have available. And in the case of chlorine, the worst case was in 1993, meanwhile in bromine was in 1999. In this case, everything is compared with a reference year that at present is 2020. And as you can see here, there is a clear reduction of these gases in the comparison. And also it's worthy to mention that the natural components, the part that is coming from natural components, is not changing a lot along the 2 years. This means that the reduction is coming basically from the human emissions and the human contributions, meaning that the measures that the protocol was emphasized and promote are working and are successful. And if you can go next, please. And also our confidence in the achievements of the Montreal Protocol is really continuing, and it's based on the sustainable networks of monitoring that we have now. And also is covering, like, from 1980, you can imagine that we are covering now more than 40 years of observations. And this allows us to establish some trends. And it's in this image that you can see that there is an evolution of these different components, and here is plotted, displayed the UV index. Why? Because sorry, I think that I was expecting another slide. Then this is the evolution along the years of the different components, and here you can see also how is the evolution of the UV index along these years, considering different conditions. What will happen if there had no agreement in the Montreal Protocol? If we were assuming an annual increase of these components that we saw before, that are the stratospheric chlorine, for example, some scientists have shown using modeling, not just observations, but using modeling for doing projections, that the UV index radiation, that is one of the things that is more harmful for our health, has been increased in a measured way with catastrophic consequences, particularly in high latitude. And this is what you can see basically in this dark line, the black one, that is showing the projection on how the UV indexes was really growing very fast if there were no intervention. If you can go next, please.
Yes. So I will take over now.
So for you, this one.
What did we observe in the atmosphere in the end, thanks to the decision about the Montreal Protocol from 1987 and onwards? So this is the time series of the ozone hole extent. So the maximum extent of the ozone hole each year since 1979. So it's a data set that is combining data from C3S, the Climate Change Service, and CAMS, the Atmosphere Monitoring Service, for the year since 2003. And what you can see is that after the phase that I have already showed in the late 70s and 80s, where the ozone layer developed, you can see that there was a period in the late 90s and 2000s where year after year each of the holes were pretty large. So you have a large zone of blue colors. And since the 2010s, even if there is quite a large variability from year to year with ozone holes that were pretty big, at least we are on a trend of certainly stabilization and decrease. And with what Sara showed about the chlorine and bromine content in the stratosphere, we know for sure that at some point, so in the 2060s, we can expect this ozone hole to disappear. Another way to show exactly the same data is as a function of the years, the area, the maximum extent of the ozone hole along the years since 1979. So you can see how the ozone hole episode developed until the mid-90s, and then it's plateauing and starting to decrease. Actually, when you look at the maximum extent in terms of ranking, you see that with the exception of 98 and 2015, most of the other ones are in the 2000s. What you can see also is that the last three ozone hole episodes, so 2020, 2021, and 2022, they are not at the top, but they're quite close, and I will talk more about this later. But before doing that, what I would like to do at this point in the presentation is to show you a little video that will recap a little bit what we have said and also explain to you in a quite compact way what are the drivers of the ozone hole destruction during the ozone hole episode. So it's a small 3-minute video.
Ever wondered what happened to the ozone hole? A few decades ago, it was the prime example of man-made environmental damage. Today, you hear less often about it. Did it just go away? Let's recap. The ozone layer lies in the stratosphere, where it acts as a shield to protect us against harmful UV radiation, which, in excessive doses, can increase your risk for a number of diseases, including skin cancer. For decades, the ozone layer was attacked by invisible enemies, chlorine, bromine, and other halogens, at the time commonly used in aerosol propellants, refrigerants, pesticides, and solvents. Under ultraviolet radiation in the atmosphere, these substances break down and react with ozone, destroying the Earth's protective ozone layer. But, to answer the original question, what happened to the ozone hole? The 1987 Montreal Protocol happened, This international treaty agreed to phase out the substances which play a role in ozone depletion and was ratified by 196 states plus the European Union. End result? The trend over the last 5 to 10 years has been no increase in the Antarctic ozone hole. However, each year in September, the Antarctic sees a resurgence of the ozone hole. This happens because during winter, the entire polar region is in darkness and a powerful wind pattern called vortex develops. This vortex isolates the polar region from the rest of the atmosphere and causes temperatures to fall below -78 degrees Celsius, at which point polar stratospheric clouds form. Displaying majestic colors, polar stratospheric clouds also have a downside. Their ice crystals boost chemical reactions between ozone, chlorine and bromine. The European Union's Copernicus program monitors stratospheric ozone using satellite observations and modeling, similar to weather forecasting, to give us a clear idea of how the ozone layer is healing over time. Currently, estimates suggest it will be 2060 before ozone production returns to pre-1970 levels. Good science, early discovery and monitoring means it is possible to take action and repair man-made impact on our world.
So with this little video, so you had a recap of what we've said already, but also you had more insight on what happens specifically in the polar region and the role of the isolation of provided by the polar vortex and the night. Another element that was brought into the video is the capacity that satellites have to monitor ozone. Actually, the ozone is a molecule that absorbs radiation, as I mentioned already, and that sits actually in between the satellite and the Earth. So it can be measured by satellite very accurately. And actually, we have measurements of ozone from satellites since the late 60s and since 1979 continuously. And that's why the graphics that we've been showing to you generally start in 1979. So on a daily basis, CAMS uses ozone from 6 different instruments, including chiefly our own Copernicus Sentinel-5 precursor. You have a snapshot of a particular image from Sentinel-5 precursor, which is one of the key ingredients that we use at ECMWF to combine satellite observation and modeling to give a complete picture of the ozone layer. So how we do this, it would be too long today to go into detail, but what we've done is that we've included chemical processes into ECMWF numerical weather prediction model. And together with ozone observation from satellite, we use around 80 additional observations covering the weather, the cloud, aerosol, to deliver these products. So this is what allows us to show in real time what's happening to the ozone layer. And here I will launch the animation of last year's ozone hole event, which started in winter for Antarctica and developed. You can see the development while the video is running. The areas which are below 220 Dobson unit appear as clear. So you see here the ozone hole that is very much formed. There are, as Sara mentioned, thanks to the Global Atmospheric Watch program, ozone sondes that are launched in different places in the world, and in particular in the South Pole by the American agency NOAA. And you can see how the CAMS profile for the 1st of September in yellow and the 1st of October in red, so that's during the ozone hole episode, match actually very well with the sondes which are in black and gray. So the data has very high quality and so can be trusted to monitor how the ozone layer is developing. What you can see in the bottom line of plots, I will only comment the one about the ozone hole area, is how between 1979 and 2022, the extent of the ozone hole has evolved between winter and spring. And what you see is generally the ozone hole starts to form in late August and September, peaks around end of September and October, and then disappears generally all before December. So that's the climatology of what happens. And actually, over the last 3 years, there was something quite unusual. So the ozone hole started normally. I would say it's in the middle of the pack. But what is quite clear, so they reach pretty large extent. So not the maximum, the absolute maximum, but quite a large extent. And then they lasted much longer than was seen in the past. So in particular, the 2020 ozone hole lasted until after Christmas, which had never been seen in the past. And we are looking into the reasons for this late disappearance of the ozone hole episode in 2022, and this has to do probably with the fact that the dynamical condition and the very low temperature, probably connected to climate change, has something to do with it. However, it's not changing in any way the perspective that in the end, the ozone layer will recover and the ozone holes will disappear, simply because the fuel in the agent of the ozone hole, which are the bromine and chlorine compound, now are at bay and are reducing, as Sara was showing. So it's nice to talk about the ozone layer, but it's up above 25 kilometers above our head. But it has also practical implications down here on Earth. And one of the key implications is health. As you already know, overexposure to UV radiation is very bad for health, with lots of consequences from skin cancers to diseases with eyes, like cataracts. And in order to characterize UV exposure, United Nations have organized a program to define these UV indexes, which is a weighted function of the solar radiation that comes at the ground, weighted by their dangerosity for human skin. And this gives an index that varies from 0 in the night to maybe 20 or 22 in the tropics. In general, it's communicated up to 11, because already above 8, it's very high UV conditions, and exposure should be limited to the maximum. So CAMS produces on a daily basis monitoring and forecasts up to 5 days in advance of the UV index. This is an example actually for today. It's a forecast that was done yesterday, focusing over Africa. You can see two different products. One product on the left, which is showing all the effect on UV index, including the clouds. So that's why you have in some places fairly low UV index values. And on the right, you have all the effects except the one of clouds. And the reason is that the forecasting of cloud is very difficult. As you experience, there may be clear sky in between the clouds, so that for communicating the UV index, we use both the UV index with the effect of clouds and the UV index without the effect of clouds, which we call the clear sky UV index. And you can see that in the southern hemisphere, it's now summer, the values of UV index are pretty large, in particular over the eastern coast of the western coast of South Africa and Namibia. Actually, Sara will be talking more about UV index and how it is used in the context of a global application. But before giving her back the floor, I wanted to mention that actually UV radiation is not only important for human health, it's also important for a number of activity sectors. And in CAMS, we have many users requiring UV radiation information for different applications. I will mention in particular indoor crops. UV radiation is a key ingredient to photosynthesis, and companies growing fruits, especially soft fruits, need very accurate information about what is called the photochemically active radiation, which is a different weighting compared to the UV index, specifically adapted for plants, in order to manage greenhouse, the venting or the shading of greenhouse using Copernicus and CAMS data. So it's also the case for outdoor crops, of course, that are affected, and biodiversity that is also affected by UV radiation. And taking another example from a complete different domain is, as you've all experienced, plastics especially age rapidly outdoor, and this is also because of UV radiation, and part of our users are using CAMS information to study how these plastics or different types of plastics are aging. But I hand back now to Sara for a specific example of one of the applications using CAMS data.
Yeah, thanks a lot, Vincent-Henri. As you can see in the screen, is a smartphone app called Global Sun Smart, and it's basically focusing on the impacts of the UV in the ultraviolet light in our health, particularly in our skin, eyes, and basically our health. And this app was launched in 2021, and it was supported by the Cancer Council of Victoria in Australia, but also has the support of WMO, the World Meteorological Organization, WHO, the World Health Organization, and also UNEP, the United Nations Environmental Program. Basically, this app is available for Android, but also for Apple devices, and you can download freely and install in your tablet and a smartphone. And the goal of this app is basically help to the individual persons to really know when they have to use some protection measures to reduce the impact of this to this UV potential damage in our health. Try to avoid some skin cancer or other melanoma affections, that is basically skin cancer. The app is giving you a forecast of 5 days of UV and weather forecast, and also is suggesting you some measures of protection if you are in a location where there is a value of this UV index that Vincent-Henri mentioned above 3, because this is the number that you have to start to be worried if you look at the scale, because below 3 is quite safe, is normal values, but if the forecast or the news that you receive is above 3 is when you have to start to do some actions. Also, basically, the forecast that you are receiving from this app is coming from the Copernicus UV service, and is all the products that Vincent-Henri mentioned in the previous slides. And also, one of the advantages is that the app is available for different languages, not just English, it's also Chinese, French, Russian, Dutch, and Spanish. Then it's having more access to the potential users that wants to use this information. And also, one of the important features of the last version, if you are coming from New Zealand and the Southern Hemisphere, is that you are having access to near real-time data that is measured from the networks in this area. If you can go next, please. Here you can see some examples from yesterday of 4 locations, because the app is allow you, if you see in the bottom of these screenshots, there is one bottom that call it locations, and you can choose your current location, but also you can check what is happening in other parts of the world. Here you can see Geneva and Bonn, because I'm based in Geneva, and then Vincent-Henri is now in Bonn, but also we put some examples of Rio de Janeiro in Brazil in the Southern Hemisphere, and Darwin in Australia. As you can see, basically what you can see from the app is that is the time range of the solar hours, that basically is early morning to late afternoon, and the dot is telling you in which moment of the day you are. And if there is starting to be something orange is when you are starting to be worried because the forecast is telling you that you will be above this 3 UV index during this day. Then it's telling you the moment of the day, the window of the time during this day that you will have this exceedance of this value of 3, and also suggesting you what are the best measures that you can take into account when you are going outside your house, your work, out in outdoor spaces for prevent any damage that this high UV index can cause to you. Also, it's possible to receive some individual alerts, or you can keep us informative. If you go next, please. Basically, one of the big discussions that is now ongoing in the community of policymakers and also public health responsibles is this balance between what is good from the UV part and what is bad for our health. Sunburn, for example, is well known that is a risk that can cause the skin cancer. But on the other hand, we have to expose our skin to this UV solar radiation because it's basically a factor that is helping us to produce vitamin D. Then this is something good for our health. Then we have to balance the amount of solar irradiance that arrives to your skin because it's necessary to receive some sunlight, but not so much. And this is what is trying to summarize this figure that you have in the right part of your screen, and is an example coming from one author, Mackenzie and co-authors. Is focusing the study in New Zealand, but can be applied to any part of the world. And basically here you can see the relationship between the exposure in time to under this strong UV sunlight and the potential damages and benefits that you can receive from this exposure versus the intensity of this irradiance. The reddish colors in the bottoms is when you start to have to be worried because you are so much exposed, and probably this can cause some problems in future related with skin cancer or eyes irritations. And in the darkest blue is when it is a good balance between what you are receiving as sunlight and the exposure that you have. And probably sometimes it's insufficient and you will have a problem of production of vitamin D. Then what will be the best, it is the white area that you can see in the screen that is trying to balance the exposure versus the intensity of the sunlight. And it's because of that balance that sometimes is difficult to achieve in a proper way, where the public health stakeholders are recommending different things depending on the country and the region where you are. And not always is bad, not always is good, and you have to be worried about the amount of sun that you are receiving in your skin, because this is the main important message, I would say. And just to conclude, because I think that we are running late to the webinar, I will ask to go for the conclusions slide, Vincent-Henri. And if you want to contribute, you are welcome. But basically, today, Vincent-Henri, in the first part of the talk, show you how is important the ozone layer and the essential that is this element of the atmosphere is in our life, not just for Earth, also for our lives. And it is also shown that this layer will be altered by the human activities because of emissions in traffic and industry from the last centuries. Also, how the measures that are promoted by the international community, like the Montreal Protocol launched in 1980s, was helping to recover this layer, and is expected to be totally recovery in 40 years ahead. Also, it's important to be aware that the programs that are monitoring all these elements of the atmosphere is helping us to really define the status of the ozone layer, but also the ozone depleting substances that we have to take into account when we are doing this analysis. And also, it's important to support the scientists and the technicians that are keeping these stations alive and providing us this information that is fundamental for assess the interactions and the impact in our life. Also, it's important the integration of satellites that are the new generation of satellites are providing us very accurate information in a spatial distribution about how is evolving the different components that are affecting the ozone layer and the ozone hole, but also integrating the modeling information to this synergistic approach is fundamental for achieving the current status of what is going on, but also future projections and how potential measures can benefit to mitigate these impacts. Also, it's important to provide information to the users and citizens and public stakeholders for helping them to really go for decisions and establish some measures that will reduce the impact of the harmful part of the depletion of the ozone layer in our lives, basically how we can manage the UV radiation in our daily life. And in this case, apps and access to the public, to the available information is really fundamental. And this is the example that we show you today with this Global Sun Smart application that was developed in this context of collaboration is a good example. And with this, I want to thank all of you for being here today. Sorry, because we are a little bit late that we expected. And I will pass the floor to Sofia, that is our chair today.
Perfect. Thank you so much. First of all, can you hear me?
Yeah.
Yes, very
Perfect. For our audience, we had some issues with my voice before, so I just wanted to check. So thank you so much, Vincent-Henri and Sara, for this extremely interesting presentation and for dedicating all this time to us. So now we open the floor to the audience. In case anyone has questions, we still have some minutes, so you can ask them. You can either put your question on Slido or raise your hand. And in fact, I see that we have someone who has raised their hand. I've requested you, Anna, you can unmute yourself now.
Yes, you can hear me?
Yes, we can.
Okay, I have a question for the doctor, Sara. It's about the last slide. When in the diagram is the good-like zones. This is the best zone in terms for the exposure for obtain D vitamin.
Is the relationship between the time, take care because the time is in logarithmic scale, as you can see. Is the relationship between of the time that you are exposed to a certain index. As you can see here, the UV index is going up to 11 because up to 11 it should be very harmful. But the important thing is that you have to be aware that this logarithmic scale then is telling you that if you are exposed to UV index during less than 1 minute, this is not really harmful for you, and then you don't need to do anything. But if the time of exposure is growing, and then also the index is when you have to start to prevent that the UV can affect your skin or your eyes.
And doctor, the relationship between the app and this expression of the Goldilocks zone is proportional because one is logarithmic and the other is only losing. I think.
you can ask, you can tell, you don't say doctor, just tell me, Sara.
Okay. But it's a good reference, no?
In fact, the app just is telling you about the UV index, just to tell you that you are under UV index during the day that can be as a maximum 6, 7, 8, 11, or 1 or 2. But it's not considering the time that you are exposed to this index, UV index. It's just telling you what is the forecast is telling you that you will have.
Thank you very much. Very interesting, your conference. Thank you. And thank you to the doctor.
Thank you, Anna, for your question. I see we have another raised hand. Liana, let me. Oh, give me 1 second. In the meantime, as I find her again, we have another question, which is, could you say a few words about why the ozone hole stayed so long in the last few years?
Yes, I can comment on that. Actually, if you go to the CAMS website, atmosphere.copernicus.eu, in the news section, we have written an article about this to try look what was different in the last 3 years compared to to the past 40 years. So what clearly appears is that the temperatures were extremely low, and there is actually a role. The fact that ozone is low and the temperature is low is a self-supporting loop. So the lower the ozone, the lower the temperature. And because temperature were low and ozone was low, it induced a longer duration of the ozone hole. We don't know exactly why it's 3 years in a row, because as you've seen in some of the plots, there is quite a variability from 1 year to the next, exactly like for weather. What we know is that there is a trend. What we measure is that there is a trend of temperature decrease in the stratosphere, which is actually the opposite of what we see at the ground, and it can explain very well with the greenhouse effect. But it's still puzzling, and there is lots of active research to try and understand why 3 years in a row we got these fairly large, so not record large, but fairly large and long lasting. So for more, please read the news article on the CAMS website.
And Stefan, before I give you the floor for your question, before Liana had her hand raised, let's see. Can you hear us? Liana? We cannot hear you. Maybe in between, Stefan, you can go ahead and ask your question.
Yeah, small question. A year ago or a year and a half ago, I remember seeing in the news that a very significant emission of ozone depletion substances had been recorded in Vietnam. I never saw anything following that. Do we know what happened, and is there an explanation?
In 2000?
18.
A year ago or a year and a half ago.
I think you may be referring to this article, which had quite some impact.
Yes.
So there was, as Sara explained, a detection of increasing levels of CFC11 in different monitoring sites, and then there was a forensic work to try triangulate where the source might be. Actually, I think in the end it was more a province of China where it was traced back, and then the facilities involved could be found. So thanks to the monitoring that first detected that something was going wrong, because under the hypothesis that the Montreal Protocol was fully enforced, that should not have been the case. The increase have been monitoring, then modeling has been used to triangulate where these emissions would be coming from, and then action could be taken to remove these emissions. But it really shows that monitoring is essential, because otherwise, if we didn't monitor CFC11, maybe in some years we could have seen again ozone hole on the increase, and have basically reacted too late, because as is clear, you've seen that all these emissions that have been stopped essentially in the 90s, it will take still 40 years to get back to normal. It's very important to detect rapidly any unwanted, unallowed emissions, so that action can be taken immediately.
Thank you. In fact, I'm not a
So-
regular reader of Nature. I should maybe, but I had seen it in the general public news, and as often, journalists sometimes report on an event, but they fail to get back on the explanation once the origin of the incident has been identified. Thank you so much.
There is another article in Nature as well with the explanation.
Oh, I promise I will look for them and read them. Possibly
Also,
even
just
write
to
something for social media on the story.
just for complementing the words of Vincent-Henri about the monitoring, the important thing is the international collaboration for global monitoring, because what is happening in China is having implications in Antarctica, you know, and then it's really, really important to create these global networks, coordinated networks with the same standards, with the same protocols and quality controls to have homogenized information that we can use really to assess these connections that looks like far away China from Antarctica. And at the end, you know, you can see that they're really connected.
Going back to Liana, let's see if now you can ask your question. We still cannot.
Hello.
There you
Hello,
go.
this is
Yes.
Liana speaking. Can you hear me all right?
Yes, perfectly.
Wonderful. I'm the national ozone focal point of Armenia. And in Armenia, we have a WMO Global Atmospheric Watch Station number 410. And my question is on whether the satellite measurements of the ozone layer shall be considered as complementary to the ground-based ozone measurements, or whether they can be replaceable. And what would be the added value if in Armenia we will launch the satellite measurements? I'm sorry for asking this question, which may be a very simple one, but still we are not clear, and I definitely need the clarifications from specialists. Thank you.
Sara, you want to start maybe?
Yeah, I will start and then you will pop in. And basically, satellites need information from ground to be sure that the retrievals that they are producing for us, that is giving us this global perspective, are current with the things that we are measured from ground, and there is some currents. Also, keep in mind that satellites are using optical properties to derive information about reactive gases or aerosols, and somehow you need retrievals that needs to be calibrated with the most accurate information that we have available, that is basically coming from networks on ground. Then really is basic exercise to really check that what is coming from satellites and what is coming from ground observations is current, because this gives us more confidence about the use of satellites for the global picture, and then to integrate this information with the stations. I think that it will be a fantastic exercise if you can provide feedback if the products of the satellite over Armenia are current and working. Also, if you can use Copernicus forecast products, I think that Vincent-Henri also will support the comparison, just to see if the forecast and the products that you have available also for the modeling community, for providing you forecasts in advance, are really accurate and detailed information that you can use for your daily life. And I think that this is the philosophy that we are following, all of us, the integration of the information for providing the most close to real information about the status of the different elements of the atmosphere in the best way.
Yeah, so you said the essential. What I would like to add is that actually there are three pillars to having a complete monitoring. So the in situ, because it's ground truth, when you have a sound like this that goes in the atmosphere, it's really measuring what's happening at this precise spot. So you have very accurate observations. Satellites, they're wonderful as well, but sometimes they miss some aspects. Actually, when the ozone layer, the ozone hole first appeared, the engineers in the satellite sector, they were not expecting these low values. So for some years, they filtered out the information. They were thinking that the instruments were not working. And it's after the ozone hole has been discovered that they said, oh, by the way, maybe our data was correct. So in situ, satellite and numerical models. And actually, without the numerical models, it's actually very difficult to compare the satellite with the sound. And if you use this trio as we do in Copernicus, you can do a comparison like the one that I showed, for instance. Here, this small one, where you see sounds, so from the ground, here in South Pole, but similar to the one that you do in Armenia. and the colored lines, which are for the corresponding dates, the products which come from satellite and numerical models to this comparison. It works really well, but the conclusion is not that we don't need the sound. The sounds are essential, and the ground-based remote sensing as well, to make sure that everything is accurate, and exactly the same as for numerical weather forecast. So for numerical weather forecast, there are satellites, there are numerical models, but the in situ measurements and the radio sounds are also essential ingredients to the quality of the weather forecast in that case that we have.
Also, for complementing about modeling, what is good from modeling is that you can see in your lab, that is the numerical model, what will be the effect of some interventions. I mean, you can tune the missions and see what will happen if you are confident in your model. If your model is really a good tool for predicting what you really see in your area, then you can use this model also for doing your assessment about potential measures that you can impose and see the effect in the atmosphere. And this is also very key to integrate all the information, because if you have good tools, you can help to take decisions also to the stakeholders and policymakers. Because switch to impose that the people is binded to use the car or to reduce emissions is always like a hard decision, and all the information that we can provide to the person that has to take the decision is probably the best thing that we can do as researchers. Yeah.
Thank you so much for the the detailed explanation, and I see that Liana thanks you as well. We're a bit over time, but if you don't mind, I would actually like to ask you one tiny question. Being from the Southern Hemisphere myself, I was wondering if, like with the Cancer Council in Australia, if there are any synergies being captured with health organizations in the Global South to raise awareness of this UV app, particularly given that it's the most affected region by the...
It is WHO involved in this effort. Then I would say that in theory, it's well announced by all the United Nations channels that this app is providing you global UV forecast. Then probably, if in your region you are not really keen on to know if the people is using it, maybe we have to go for WHO and do some promotion.
Good to know. I'll keep an eye. Thank you so much, and for the presentation and for answering all of our questions. We're reaching the end of the 7th Copernicus webinar, and as I said, I want to thank again our speakers for such an interesting and engaging presentation, and to thank the audience for their participation and for all their questions. We hope that you learned something new today about how Copernicus can be used for monitoring and protecting the ozone layer. And if you have any other questions or comments, you can reach us through our Copernicus social media channels and also through our email. I will be sharing them in a moment. Before you leave, we would love to have some feedback from you. So we would appreciate if you could answer our final question on Slido, which is how useful have you found the content of this webinar? Let me just share with you. There you go. You should be able to see now our social media channels and our email address at the Copernicus Support Office. And thanks again, everyone, for joining us today. And we look forward to seeing you on our next webinar. And have a nice day. See you next time.
Vincent-Henri, if you have 3 minutes.
Yeah, 3 minutes.
I have something for you.